Hello everyone, welcome to ChemHelp. So today we're going to begin our process of learning General Chemistry 1. So this first lecture is called The Tools of Chemistry. So in this lecture I'm going to be going over basically some of the basic tools, mathematics that are needed to understand chemistry. This lecture will include three main topics. The first topic is introductory definitions. This topic will consist of defining what an atom is, defining what matter is, defining what a chemical change, a physical change is. So if you at any chance need to skip any of these sections in order to go to a section that you want to review, I will have the times in the description of the video. Next, we'll go over some sig figs, which I know is a difficult topic for many freshman chemists. And then we will lastly do some dimensional analysis problems. We'll do an easy one, a medium difficulty one, and a very hard dimensional analysis problem. So with that, let's start lecture number 1 with some introductory definitions. So, what is chemistry? What is chemistry? Chemistry is just the study of matter and the changes. This means changes. Whenever I write a triangle, that means changes that it undergoes. So chemistry is the study of matter and the changes that it undergoes. In other words, it studies how the properties of matter, it studies different structures, it studies the transitions that matter undergoes, the chemical reactions, many different things. So at the heart of chemistry is matter. So what is matter? Matter is anything that has mass and volume. So what is mass? Mass is basically just a measure of how much matter is in a substance. So it's simply just a quantity. It's a measurement. Now, the important thing to realize about mass is that mass is constant. In other words, mass doesn't change when you change the environment. So what do I mean by that? So let's say you weigh around 80 kilograms on Earth. Now, if we transported you to the moon, your mass would still be 80 kilograms. If you were put on Jupiter, your mass would still be 80 kilograms. Mass is just a measurement of how much matter is in a substance. It is independent of the environment. Now, weight is a little different. Weight takes the environment into account. So weight, you can actually just think of weight as basically the force that is applied on you by the body that you are on. So weight is basically the force that Earth is putting on you when it pulls you towards its center. So we don't need to know that for chemistry, but just know that mass is a measurement of how much matter is in a particular substance. So, what is matter made out of? Matter is made of atoms. So, atoms. You've probably heard this term before in high school or just by watching TV. What exactly is an atom? So let's change color here. So atoms. Now, atoms are probably some of the most important things in chemistry. It's what chemistry surrounds itself around. Chemistry is all about atoms. Atoms are the building blocks of matter. So atoms are what make matter matter. They are what make a desk a desk. They are what make you you. They are what make air air. They make up matter. Now atoms themselves, even though they're very small, they're made up of something called subatomic particles. So subatomic particles. So what is a subatomic particle? So subatomic particles are what make up atoms. And for general chemistry, there are 3 subatomic particles that you need to be worried about. The first one is the proton. Now the proton is a positively charged, so this stands for charged, species that weighs around 1 atomic mass unit, or 1 AMU. So hold on, what is an atomic mass unit? Well, 1 atomic mass unit is equal to 1.66 times 10 to the negative 24th grams. 1 atomic mass unit is equal to 1.66 times 10 to the negative 24th grams. So an atomic mass unit is very, very small. And that's why we use atomic mass units to describe the mass of some atomic species and not grams. Because imagine saying that a proton weighs 1.66 times 10 to the negative 24th grams. It's a lot of words. So instead we just use atomic mass units. So that is what I mean with 1 AMU. So the next subatomic particle is the neutron. The neutron is a neutral species, meaning it has no charge, that weighs around 1 AMU as well. And then the last subatomic particle that we need to worry about in Gen Chem is the electron. Now the electron is the opposite of a proton. It is a negatively charged, remember this means charged, species that weighs around 5.5 times 10, this is a point here, 5.5 times 10 to the negative 4th atomic mass units. So an electron is very, very small. So where do all these things, all these subatomic particles fit in the atom? So let's draw a very simplified structure of the atom. We'll talk more about atomic structure in a later chapter, but just to give you an idea of sort of where everything is located in the atom for right now. So let's do this. This is my representation of an atom. So we are going to point out a couple of things here. So the first thing to point out is this, oops, I don't want to use a highlighter. We're going to use our pen. So the first thing that we want to point out here is the little red dot here. And this red dot is referred to as the nucleus. So what is the nucleus? The nucleus is the part of the atom, it's in the center of the atom, which is made out of protons and neutrons. protons and neutrons. So what do you think the overall charge is on the nucleus? The answer is it has a positive charge. And the reason why is because you have protons and neutrons in the nucleus. The protons have a positive charge, the neutrons have a neutral charge. Therefore, the nucleus has a net positive charge. Now, because the protons and neutrons are present within the nucleus, the protons and neutrons are sometimes called nucleons. So, nucleons. Now, orbiting outside the nucleus are the electrons. So you have a negatively charged electron cloud around the nucleus. So this yellow part here is the electron cloud. And we're going to discuss more about this in a later chapter. So just for now, think of the protons and neutrons in the nucleus and the electrons in a cloud surrounding and orbiting the nucleus. So that's it for atomic structure for right now. So we're going to move on now into defining how these atoms interact with each other. So let's continue on with discussing molecules versus compounds. So what is a molecule? A molecule is the interaction between two or more atoms. So some examples of molecules are, so I'll just put an EG here. Some examples are oxygen gas, water is a molecule, methane is a molecule, etc. So these are all examples of molecules. Now, what is a compound? So a compound. Now, a compound can be thought of as a special version of a molecule. It's more specific, it's more exclusive. So a compound is the interaction between two or more different, so this triangle means different, atoms. So instead of a molecule, you can have two of the same atoms coming together. But for a compound, they have to be different. So some examples of compounds include water, methane, sodium chloride, and you could go on and on and on. So let's actually do a little exercise here. So I'm going to draw a little table like this, and then I'm going to put compound here. This stands for compound, and then a molecule here. This stands for molecule. And I'm going to write two different chemical species on the top here. So let's compare, let's see, let's do O2, and then we'll do CH3O. Let's actually draw this a little bit better. We'll do it this way, CH3OH. So this is methanol and oxygen. So what I want you to do is pause the video and put a check mark in the places that agree with the definition. So for example, if O2 is a compound, put a check mark in that box. If O2 is a molecule, put a check mark in that box. However, if O2 is not a compound or a molecule, put an X in that box, and do the same for both of these species. So I hope that you did that. Let's answer this question. So O2 is not a compound, and that's because you have two of the same species interacting with each other. However, methanol is a compound because you have multiple different atoms interacting with each other. Now, is O2 a molecule? Yes, it is, because you have two atoms interacting with each other. And by transitive property, methanol must also be a molecule because a compound has to be a molecule. And you have multiple atoms interacting with each other. So I hope that makes sense to you, because the difference between the two is very important, and sometimes colleges will test on the difference between the two. So now that we know what molecules and compounds are, let's now talk about the classifications of matter. So classifying matter. All right, so matter can be classified in two different ways. It can be classified in more ways, but we'll only consider two. The first is by its phase. We all know what a phase is. There's the gas phase, the solid phase, and the liquid. Let's spell correctly. And the liquid phase. All right. So let's define each of them. So a gas is a phase of matter in which matter has an indefinite volume and shape. So what do I mean by an indefinite volume and shape? So let's actually draw a picture here. So imagine that you blow up a balloon. Now, when you blow air into a balloon, the air forms like this circular shape, right? Depending on how the balloon is built or whatever. I don't know how that works, but the balloon goes into a circular shape. Now imagine you take that same air, that you take that balloon with the air in it, and then let that air out. So the balloon deflates and lets the air out. And let's say we let the air flow into a box. So here is our glass box. Now, what do you think is going to happen when we do this? Well, when you let a gas into a space, what happens is the gas actually diffuses throughout the entire room. In other words, it evenly distributes throughout the entire space. So let's say that this balloon here had a volume of around, 1 liter. In here, in the balloon, the gas occupies 1 liter and has a spherical shape. However, if we let that gas into the box, what happens is the gas expands throughout the whole space, and the gas will actually occupy the entire volume of the container. Let's just say it's 10 liters. And it will now have a cubic shape. So in this case, the volume increased from 1 liter to 10 liters, and the shape went from a spherical shape to a cubic shape. So therefore, gases have an indefinite volume and an indefinite shape. So what about solids? Solids are the exact opposite of this. Solids have a definite volume and a definite shape. So in order to think about this, think about an ice cube. So if you put an ice cube on the table, assuming that it's cold enough, and the ice cube does not melt, the volume of that ice cube doesn't really change. It also has the shape in whatever form the water took. So let's say you put it in an ice tray. The ice cube will have like this cubic shape, so it has a definite shape. It also has a definite volume because no matter where you put the solid will always have the same volume. So that's why solids have a definite volume and a definite shape. Now liquids are sort of the intermediate between these two extremes. They have a definite volume but an indefinite shape. So let's draw a picture of this as well. So a definite volume but an indefinite shape. So let's change the color here. And let's just imagine we have a cup of water. So let's just say this cup is around half full. And let's say that inside this cup is around 10 milliliters of water. Now let's just say I take that water and then I spill it in a bathtub. So let's draw a huge bathtub. And let's just say you could see through the bathtub. Now when I pour that water into the bathtub, the water will take the shape of however much volume of the shape that the water occupies. So the shape is indefinite for water, but its volume is the same. 10 milliliters of water was in the cup, and when 10 milliliters of water was poured into the bathtub, 10 milliliters of water is in the bathtub. So therefore, liquids have a definite volume, but an indefinite shape. All right, so the next thing, remember we were talking about classifying matter. We can also classify matter by its purity. So in other words, how clean it is. So it's purity. Oops, not pure, purity. So, what is a pure substance? Well, a pure substance is a substance or a piece of matter that contains only one type of compound. So this symbolizes compound, molecule, or element. So an element is basically a substance that contains the same type of atoms. We're going to talk more about elements in the next chapter. But a pure substance is basically a clean piece of matter. So a great example of a pure substance is water, pure water. So if you ever see distilled water in the store, that's very close to a pure substance because there's nothing else in there except water. So that's all a pure substance is. Now, the difference between a pure substance and there's two types of purity. There's pure substances and then there's mixtures. So what is a mixture? Well, a mixture is just the mixing of two or more substances. Different substances. So this is different. Different substances. So a good example of a mixture would be a salad. So let's discuss this for a bit. So when in your salad bowl, you have your leafy greens. You have maybe some tomatoes if you like them. And then you have your dressing. We'll just pretend it's ranch or something. You have your dressing. So in here you have solids, liquids. So you have all of these different substances mixed together. And there's actually two different types of mixtures. The first type of mixture is something called a heterogeneous, hopefully I'm spelling this right, mixture. So a heterogeneous mixture. So a really good example of a heterogeneous mixture is a salad. Because a heterogeneous mixture is a mixture in which the substances usually don't mix well together. They can be in different phases. The composition is not the same throughout the mixture. So a great example would be a salad. Oil and water mixed together is a heterogeneous mixture. So the composition is not the same throughout. The second type is a homogeneous mixture. Homogeneous. I think this is how you spell it. Let's see. So a homogeneous mixture is a little bit different from a heterogeneous mixture. So a homogeneous mixture, actually homogeneous, this is spelled wrong. So let's fix this. I'm sorry. There's an E here. I'm not a good speller. So then homogeneous. So homogeneous mixture. So a homogeneous mixture is a mixture in which the composition is the same throughout the entire mixture. So a great example of a homogeneous mixture is actually alcohol and water. Because if you mix alcohol and water together, you'll get one nice solution. And it's all a liquid. The composition is the same throughout. So a good example is alcohol. This is actually ethanol. This is the alcohol that you drink. And water. So another name for a homogeneous mixture is actually a solution when it is in the liquid, when it is in the fluid phase. So a homogeneous mixture in the fluid phase is actually called a solution. And fluid actually does not just mean liquid. Fluid is actually a physics term, and fluid is basically, it consists of both gases and liquids. So both gases and liquids are considered fluids. So those are the two types of mixtures that you should know. So with that, we're going to discuss one of the last things for the introductory definitions, and that is the properties of matter. So we're going to talk about the changes in matter, not properties. So changes in matter. And there's two types of changes that you should know about for Gen Chem. The first is a physical change. Now, a physical change is basically a change. Remember, the triangle is a chain, it means change, is a change that does not change the chemical composition. So great examples of physical change include melting, boiling, freezing, etc. So things that don't change the chemical nature of the substance. The second type of change is called a chemical change. Chemical change. So a chemical change is a change that changes the chemical composition of the substance. So chemical changes will be basically every single chemical reaction that we see. So a great example of this chemical change is actually what occurs when you use a Bunsen burner. So you may have seen Bunsen burners on TV before or on different lab shows. So all a Bunsen burner does is it reacts with the help of some fire or a match. We'll discuss this actually in Gen Chem 2, why you need a match to set a fire. Well, one of the chemical changes is actually when you react methane with O2 gas, and you may have seen this in Bunsen burners. When you put a match over this methane gas, it causes a flame to erupt. So the chemical reaction that's actually taking place in this process here is this chemical reaction. And we'll go over this type of stuff later on. So 2H2. It's a combustion reaction. It's basically reacting methane with oxygen to form CO2 and water. So this is called a combustion reaction. So if we just look at the carbon, in this case, if we just look at the carbon atom, we can see how the composition changes. And here the carbon is attached to 4 different hydrogens. However, if we compare it to this carbon and the carbon dioxide, it's connected to 2 oxygens. So the chemical composition is changing. Therefore, you have a chemical change. So those are the 2 types of changes in matter that you'll deal with in chemistry. All right. So the last thing that we are going to talk about is precision versus accuracy. So accuracy versus reliability. Accuracy versus reliability. Now, these reliability and accuracy have 2 different names, actually. Accuracy is also given the name validity. And reliability is sometimes also called, it's usually called, actually, I should have used precision instead. So accuracy and precision. So accuracy describes how correct your measurement is. How correct your measure is. While precision basically measures how reliable your measures are, hence reliability. So how close they are. So I think a really good way to show the difference between these two is through a classic figure that you'll see in almost every single textbook out there. And that is the dartboard figure. So here we have the bullseye in the middle, where the bullseye is where you want to hit. So the closer you are to the bullseye, the more accurate you are. So the first case is a high precision case. So case 1. In this case, we have high precision because the dart thrower is throwing the darts in pretty much the exact same position. Now, this condition is not accurate because it's not at all close to the bullseye position, but they're all very close together. Therefore, it's very precise, very reliable. The second condition looks like this. Now, this measurement is accurate because it hit the bullseye, but it's not precise. You don't know what you're going to get when you throw the dart. It could go here, it could go there, and it could go right to the bullseye. Therefore, it's accurate, but not precise. We want our measurement tools to be both accurate and precise. So we want them all to be precise in hitting this bullseye. Therefore, they're both precise and accurate. So this is what we aim for in the lab. And hopefully you'll get that in your lab courses when you do your experiments. So that is actually it for the introductory material. So now what we're going to do is we're going to shift our focus to more of the mathematical tools that you will need in order to do well in your chemistry courses. So let's begin by discussing significant figures. So significant figures. Let's change the color here. So sig. Oops, I don't know what happened there. Let's erase that. Significant figures. Now, a lot of kids get confused by sig figs. And I will admit that when I was in general chemistry, I was very confused by them at first. However, the best way to get good at sig figs is to practice. So I encourage you, after you watch this video, to go into your textbook and practice some problems, because that's the only way you're ever going to understand sig figs or dimensional analysis or even anything in chemistry. Chemistry is not like any other science course. It's one of those sciences where you can't memorize. You can't memorize and do well. You need to practice. You need to practice put different problems in the back of the book in order to do well. Because a lot of chemistry is not just reiterating what your professor says. It's not just copying down and basically expelling all this material that you memorized. It's a lot of analytical questions. So it's a lot of things where you're going to use what you learn in order to problem solve. And the best way that you can practice with that is by doing practice questions. So I please urge you to do practice questions. That's that's the best shot you have at getting an A in any of your chemistry classes, physics classes, etc. So please do practice problems. I can't urge you enough to do them. So after that, let's get into these sig-fig rules. So first of all, what is a sig-fig? A sig-fig literally means important figures, important numbers. That's all it means. All sig-figs are pointing out what the important numbers are in a measurement. Now, the important thing to note is that the more sig-figs you have, the more precise the measurement. And we'll see why later on that's the case when we actually do some of these problems together. So we'll just leave it at that for right now. The more sig-figs you have, the more precise the measurement is. Okay, so let's get into these rules. Now, a lot of these rules are better to show, so I won't be doing too much writing in this part, but I will be talking slowly and explaining what I'm doing. So there will be a little bit less writing in this part. So how do we begin to count the amount of significant figures? So let's just come up with an arbitrary number. 0, 0, 1, 3, 4, 0, 5. This is a random number I came up with. All right. So we want to figure out how many significant figures are in this number. How can we do this? Well, the first thing we do is start counting from the left. So we'll start on this side. So we start around here. We'll start here. But we have to take some things into account here. The second rule that you must know is that zeros at the beginning of a number are never, I'm going to emphasize never, significant. Therefore, you should never count the zeros at the beginning of the number. So these two zeros in front of the 1 are insignificant. However, zeros in between two non-zero numbers are always, just wanna, okay, are always significant. I'm just gonna abbreviate significant like that. So let's see why. So let's look at our little example here. So 1, 3, 4, 0, 5. Okay. So we know that these two zeros are not significant. Why? Well, it's actually because we can translate this into scientific notation, right? So if we translate this to scientific notation, this is around 13,000, right? So it'll be times 10 to the 4th. Those zeros aren't even there. You don't need those zeros to get the same value because you can also write it like this. So therefore, we don't count these zeros when we count the number of significant figures. So you can just cross those out at the beginning. So we technically start here. We technically start at the 1 here. So, and we start by counting from the 1 and on. So we have 1, 2, 3, 4, 5. So here we have 5 sig figs. 1, 2, 3, 4, 5. Yep. Now the 0 at the 5 is the 0 between the 4 and the 5 is very important, because you can't express this in scientific notation without that 0. Because if you remove that 0, we'll use this, if you remove that 0, you get this, which is not the same value. So that 0 is significant and should be counted. So that's why this has 1, 2, 3, 4, 5 significant figures. So once again, in order to count the number of significant figures in a measurement, you start counting from the left of the number. So you would start counting from this side. Zeros at the beginning of the number are never significant. And then zeros in between two non-zero numbers are always significant and should be counted. So that's basically all the rules you have to know for counting significant figures. All right. There's also another rule you need to know for decimals, because decimals are sort of a special case, because decimals are basically used to imply how precise your measurement is. So zeros at the end of a decimal are always significant. Why? Well, let's just do a little example here. So let's just say I have two of the same values here. So 0.3 and then 0.3000. These are the exact same values. They're the exact same magnitude. This one, though, has one significant figure. This one has 1, 2, 3, 4 sig figs. Now, why do we count the zeros here and not? Why do we count the zeros here and not in the and we don't count the ones in the front? Because we can still express this in scientific notation as this. So why do we have to have these zeros at the end? Well, you should remember from the beginning of my lecture that the more sig figs we have, the more precise our measurement is. So by putting these zeros at the end of the behind this 3, we're indicating that this measurement is extremely precise. Because having this amount of zeros there means that this 0.3 is very, very close to this 0.3. It may even be exactly 0.3. So the more zeros you have after the decimal, the more precise your instrument is. However, in this case, when you have the 0.3 without the zeros after this, you're indicating that this instrument may be less precise. For instance, let's just show this with these two conditions. So let's say I have these two instruments. One instrument has the ability, one instrument produces this measurement and the other instrument produces the one we have above. So in this case, this instrument, number 1 here, could produce these values. So if it produces these values, it's safer to say that the actual measurement is around 0.3 instead of saying it's 0.31, 0.32, 0.305, because the precision is not that high for this instrument. So we can only say with confidence that the measurement is around 0.3. However, if our instrument gives us this value, let's just say the different measurements for the same thing could be this. That doesn't make. Sorry about that. Let me just wrote a little too fast there. So you can see here that the only values that the instrument can be sure of is the 0.3000. So this instrument is much more precise than this instrument. So that's why the decimals after the decimal point, that's why the zeros after the decimal point are always significant in this case, because it shows how precise your instrument is. Now remember though, when I talk about after the decimal point, I'm only talking about after non-zero integers. So if I had this, you don't count these zeros still. You only count this 0 and the 3. So in this case, you would get 2 sig figs. Because zeros at the beginning of the number, no matter what, are always insignificant. Only zeros after non-zero numbers, after a decimal point, are significant. All right, I hope that makes sense for counting significant figures. So the last thing I want to do is, for talking about counting significant figures, is what about values like 4,000 that are written like this? How many significant figures would be in a value like this? Well, there's actually only be one. And that's because we can express this in many different ways. So we can express this 4,000 as 4 times 10 to the third, 40 times 10 to the 2, 400 times 10 to the 1, or 4,000 as itself. Having these zeros after this 4 without a decimal point does not show any precision. Therefore, the zeros in this case are insignificant. So once again, let's just review all these rules one more time. So the rules are that you always should start counting from the left of the number, so towards the beginning of the number. And you start officially counting at the first non-zero integer. So in this case, you would start counting at the 1. Zeros at the beginning of the number are never significant. So if you have a value like this, or a value like this, the zeros in both cases are never significant, and you only start counting at the first non-zero integer. So in this case, you would have 1 sig fig, and in this case, you would have 1, 2. You would have 1, because this is 10. So you would have 1 and 1 right here. Zeros in between two non-zero numbers are always significant, as we showed here. And zeros at the end of a decimal are always significant. And we showed that through our example here. And lastly, if you have a value like 4,000, 100, 10, 20, you don't count the zeros here because they are insignificant, and you only count the non-zero numbers. So in this case, you would have only 1 sig fig, 1 sig fig, 1 sig fig. All right, so that's a lot of material to go over, and I think the best way that we can do this is to do an example. So right now, I encourage you to pause the video after I write out these numbers and find out how many sig figs are in each measurement. So I'll write them out for you. All right, I encourage you to pause the video and do this for yourself. So hopefully you pause the video, and let's start off with this first one. This first one is 1,000, of course, and this one measurement only has one sig fig, and that's because you can express it in many different ways using scientific notation, etc. So this only has one sig fig. The next one, remember, you start counting at the first non-zero integer. So these two zeros are insignificant because zeros at the beginning of the number are always insignificant, and you start counting at the 1. So 1, 2, 3. And remember that zeros after a non-zero number in a decimal point, so something like this, are always significant because it tells you how precise your measurement is. Now lastly, remember, start counting at the first non-zero integer, so cancel this out. Give us 1, 2, 3, 4. So you have 4 sig figs here. And that's how you count sig figs. So not too bad, right? Now, if you don't explain that, if you don't understand this, I encourage you to go back into the video and rewatch it. And if it still doesn't make sense, you should go into your textbook and see what they have to say. Sometimes teachers teach it a little different ways. I know there's different methods out there into counting, but I think this is the most efficient way. However, if you have any questions or any comments, please put them in the comments section of this video. All right, so now that we know how to count sig figs, let's go into the different rules for calculating. So let's talk about when you add and subtract. So adding and subtracting. So let's add a bunch of stuff here. Sorry, I'm just looking at my thing here. Okay. So whenever you add or subtract numbers or measurements, your resultant value that you have at the end, so whatever value you get after adding or subtracting, should have the same amount of significant figures as the value with the smallest number of significant figures. So let's write that down. After completing addition or subtraction, the final value should have the same number of sig figs as the measurement with the lowest number of sig figs. So if we were to add all these things, all these values together, you should get, when you put this in your calculator, around 4.43524. Now, we need to convert this into the correct number of sig figs. So let's count the number of sig figs in each value here. So you start at the first non-zero number. So 1, 2, 3, 4, 5, 6. So you have around 6 right here. And now these zeros are significant because they're in between two non-zero numbers. Then we have 1, 2, 3, 4. And then 1, 2. 2 sig figs here. So our final value should only have 2 sig figs. So our correct answer with the appropriate number of sig figs should be 4.4 because our value here is less than 5, so we round down to 4.4. So that's the rule for adding and subtracting. Now multiplication and division actually uses the same exact rule. So let's do a multiplication problem. So actually, let's write that down here. So 2 multiplication and division. So multiplication and division uses the exact same rule as adding and subtracting does. Your final value should have the same number of sig figs as the measurement with the lowest number. Do one example. So let's just do 300 times 2. So in this case, you have 1 sig fig, 1 sig fig. Since both have 1 sig fig and 1 sig fig is the lowest number, you would get 600, which would translate to 6 times 10 to the 2. And that would be your answer with the appropriate number of sig figs. All right, so now that we know how to use sig figs, we can apply what we know to dimensional analysis. I remember when I was in general chemistry, a lot of people had so much trouble with dimensional analysis. And when I tutor, a lot of kids have a lot of trouble with dimensional analysis. And in reality, it's not that hard. It's just converting one thing into another. But even though it's rather easy once you get the hang of it, it's very important in chemistry. A lot of math in chemistry is based upon dimensional analysis. So I think the best way to do dimensional analysis is through practice problems. So here we're going to do 3 different practice problems. Okay? We're going to do an easy one, a hard one, a medium one, and then lastly, a hard one. Okay? All right. So here's the easy one. And remember, for each one of these, we want to use the correct number of significant figures. So this is the easy one. So we'll keep the sig fig rules in mind. So if one apple equals 2 oranges, so if one apple equals 2 oranges, how many oranges will I have if I have 4 apples? Okay. So if 1 apple equals 2 oranges, how many oranges will I have if I have 4 apples? So in order to figure this out, we have to cancel some things out and multiply certain things by certain things. So let's do this. So we have 4 apples, and we want to figure out how many oranges we'll have if I have 4 apples. So in order to do this, I have to multiply this 4 apples by the conversion factor. And this conversion factor is the 1 apple equals 2 oranges. So in order to figure out how many oranges I need to cancel out apples. And I do this by putting the conversion factor in like this. 2 oranges. Because if you think about it this way, if we translate it into a 1 fraction, this translates into 4 apples times 2 oranges over 1 apple. And when I do this, you can see how things cancel out and you get another unit. So you see here that apples and apples cancels out and you are left with oranges. Therefore, you have 8 oranges. So that's all dimensional analysis is. You're just taking one unit and converting it into another unit using a conversion factor. Okay, so let's do something a little more interesting. The second example, and this is a medium problem. And I will do this for every single video. I will have an easy, medium, and hard problem. All right, so for the medium, remember that we said 1 electron is equal to 5.5 times 10 to the negative 4 atomic mass units. And we know that 1 atomic mass unit is equal to 1.66 times 10 to the negative 24 grams. How many grams is an electron? So I encourage you to pause the video and try it for yourself. All right, I hope you paused the video and tried it for yourself. So let's go on and figure this out. So if an electron weighs 5.5 times 10 to the negative 4th atomic mass units, we need to multiply this by the conversion factor. And this conversion factor is 1 AMU in the denominator and 1.66 times 10 to the negative 24 grams. So if you cancel out your units, AMU cancels out, AMU cancels out, and then you plug it into your calculator. So I'm plugging it in right now. 1.66 times 10 to the negative 24. That will give you 9.13 times 10 to the negative 28 grams. Now, we need to put this in the correct number of sig figs. So how many sig figs should we have? Well, let's count. We have 1, 2. And here we have 1, 2, 3. Now, we don't count this 1 AMU because 1 AMU is an exact measurement and people consider it to have an infinite amount of significant figures. So like if you have 12 inches per 1 foot and you have to convert something, don't look at this number for significant figures. Only look at this number because this is an exact measurement, so it's considered to have an infinite number of sig figs. So in this case, only count this part of the conversion factor. So you have 2 and 3 significant figures here, and since you only have 2 significant figures, and when you multiply something, your product should have the same amount of significant figures as the measurement with the least amount. So therefore, instead of 9.13, it should be reported as 9.1 times 10 to the negative 28 grams. Let's do it like this. All right, guys, so here is the really hard problem. So let's read this together. A gas resides in a 100 cubic millimeter container. The gas has a mass of 5 units, and the gas has a constant expansion rate of 5 times 10 to the third cubic meters per second. If the gas is moved to another container where it has a density of 0.1 grams per cubic millimeters, how long will it take to fully expand into the new container? And here I give you a few different conversion factors. So note that density is equal to the mass over the volume. 1 cubic meter is equal to 1 times 10 to the 9th millimeters cubed. And then 1 unit is equal to 10 grams. And I encourage you to pause the video to try this problem for yourself. However, I will start going over it now. All right, so let's just change the color here. Let's see, green will be good. All right, so the first thing that I want to do is let's convert these units into grams, because that will just make more sense, right? So we say we have 5 units, right? Now remember, keep track of your significant figures. So 5 units, we have 5 units here, okay? And 1 unit is equal to 10 grams. So 1 unit, 10 grams per 1 unit. And this is our conversion factor. So let's keep in mind significant figures. So here we only have 1 sig fig. Here we only have 1 sig fig. And remember, we're not counting this 1 unit because it's an exact measurement. It has an infinite number of significant figures. You can't be more precise than that. So therefore, we're only counting these 2 numbers. So 5 units, the units cancels out, giving us grams. So therefore, our mass is equal to 50 grams. And now we'll keep in mind that we only have 1 sig fig here by putting in a little underline. I'm just going to keep this 50 here just to keep us from getting confused. So that little underline means that we only have 1 sig fig. All right, so now what I want to do is calculate the density in this original container. So we know from the equations above that density, that's the symbol for density, is equal to the mass of the gas over the volume in which it was contained. So we're going to call the initial container 1, and we have 50 grams of gas in a 100 cubic millimeter container. Therefore, the density is 0.5 grams per cubic millimeter. Now let's just make sure we have the correct number of sig figs so far. So we have 1 here, and 1 in our final measurement. So this is our density in the original vessel. All right. So this next step is probably where a lot of you maybe got tricked up. Hopefully you didn't. But remember when I said that gases have an indefinite shape and an indefinite volume? I never said that gases have an indefinite mass. The mass is completely conserved in this question. So therefore, the mass of the gas in container 1 should equal the mass of the gas in container 2, right? So how can I find the volume in the second container? Well, we have the density in the second container, and we have the density in the original container. So, and we also have an equation to relate the two. So M1 would be equal to the density of the gas in the first vessel times the volume of the gas in the second vessel. And M2 would equal the density of the gas in the second vessel and the volume of the container. So in order to solve for V, we just got to divide by this density here. So density 1 times the first volume divided by the density 2 will be equal to our second volume. Now our first density was 0.5 grams over 0.5 grams per millimeters cubed. So let's write that down. The first volume was 100 millimeters cubed. And then the second density was 0.1 grams per millimeters cubed. All right. And remember, since we're dividing, we write it this way. So when we multiply all this together, let's remember, keep track of our significant figures. We have 1 here, 1 significant figure, 1 significant figure. So our overall result should have 1 significant figure as well. So millimeters cubed cancels out right here, and then the grams cancels out as well, leaving us with millimeters cubed. So when you plug this in your calculator, so I'm plugging it in now, you get 500 millimeters cubed. Now remember, keep track of those significant figures. So I'm going to put a little underline. So the second volume is equal to this. Now, what we can do is now figure out how fast the gas will take to expand into this second volume. But we first got to convert this millimeters cubed into cubic meters. So 500 millimeters cubed, and we have to multiply it by our conversion factor, which is 1 times 10 to the 9th cubic millimeters per 1 meter cubed. And then we can multiply that by the second conversion factor, which is the inverse of the velocity, which we said was 5 times 10 to the 3rd cubic meters per second. So when you go through this and cancel out all the units, so meters cubed cancels out, millimeters cubed cancels out, so does meters cubed, we are left with seconds. So therefore, and remember, we only have 1 sig fig here, 1 here, and 1 here. So our final answer should only have 1 sig fig. So therefore, when I plug this into my calculator, I get, let's see, 1 times 10 to the negative 10th seconds. So it is fast. So it fills this entire container in 1 times 10 to the negative 10 seconds. So, and recall that this only has 1 sig fig. Alright guys, so that's it for this video. Now, I urge you, I really urge you to practice what you learned. Practice. Please, please, please practice what you learned, because you will never learn chemistry without practicing. Now, I think that what we covered here today should cover pretty much the first chapter of any general chemistry book. But however, please read your textbook and please look at your professor's notes.